Hello everyone, welcome to the third episode of Humpty Dumpty series. In the second episode, we defined the Humpty point and we discussed few basic properties of it. For people who are not familiar with Humpty points, please revisit the episode 2 of the series. Today, we are going to discuss about a special property of Humpty point with respect to orthocenter of the triangle. Orthocenter is the intersection of altitudes drawn from the vertices to the opposite sides. Now, how is this related and how are we going to locate the Humpty point on the median? We will discuss this in more detail. Let's get started. This is the configuration of a Humpty point as we discussed in the second episode. It is the intersection of circle tangent to BC at B and passing through A, and the circle tangent to BC at C and passing through A. Consider BHA and AHA and also CHA. Notice that by the tangent chord theorem, angle made by the chord BHA with the tangent BC equals the angle subtended by the chord BHA on the alternate segment of the circumference. Similarly, the angle BCHA equals CAHA. Therefore, the angle in the triangle HABC at B and C are adding up to A. Therefore, the conclusion is that angle BHAC is 180 minus A. Because these two add up to A, right? As you could see here. Now, due to this observation, we get angle BHAC to be 180 minus A. And let's write this down. Alright, now consider this triangle. Consider AHAB triangle. Clearly, AB is also a chord of the circle gamma B. And therefore, the angle made by the chord AB with the tangent BC equals the angle subtended by the chord AB on the circumference. So it should be the alternate segment of the circumference. We know it is B because ABC is defined as the angle B and therefore this is B. And the angle opposite to it will be 180 minus B. Therefore, we get angle AHAB to be 180 minus B. Similarly, chasing the angle AHAC, we get it to be 180 minus C. So this is a simple angle chase and we arrive at this particular configuration of angles 180 minus A, 180 minus B, 180 minus C. These are the angles formed by joining HA to the vertices of the triangle. Alright, so let's remember this. We will need this for the future applications. Second one is about orthocenter. So we will discuss why we introduced the orthocenter here, but let's derive some angles like this for orthocenter. So consider a triangle ABC. And let us join orthocenter H to the sides or the vertices A, B and C. We will figure out these angles, which is similar to the analysis we just did. Angle BHC will be 180 minus of the sum of these two angles of the triangle HBC. Now notice that this will be 90 minus C because if I extend BH, it shall be perpendicular to AC and this angle is C, therefore the other angle will be 90 minus C by angle sum property. Similarly, angle BCH will be 90 minus B, because when you extend this, it will be perpendicular to AB, and this is B, therefore the other one is 90 minus B. So the middle angle BHC will be equal to 180 minus of 90 minus C plus 90 minus B. Well, this is equal to just B plus C, or in other words, 180 minus A. And similarly, chasing the angles, we get this to be 180 minus C and this to be 180 minus B. For example, 180 minus B can be obtained by first finding the angle CAH, that is 90 minus C, and ACH, that is 90 minus A. Therefore, it should be 180 minus B. Alright, so some two angles of this are interchanged. Let's see what are they. We know that when we discussed about the angles made by the A Humpty point, those were also equal in the magnitude, but it was 180 minus A here, 180 minus B here, and 180 minus C here. So this is our A Humpty point. And it is 180 minus B here, 180 minus C here. You could see that 180 minus B and 180 minus C are swapped. But 180 minus A stays the same. That is, we conclude that angle BHC equals angle BHAC, because only the other two angles are swapped. These two angles are equal because they stay the same, 180 minus A. And this gives us the notion of cyclic quadrilateral, because in cyclic quadrilaterals, you have this property. Take 2 points, then the angle subtended by these 2 points on any point on the circumference is the same, considering the same side of the circumference. So therefore, by the converse of the statement, we get that BHHAC are concyclic, because this is 180 minus A and this is 180 minus A. So the angles subtended are equal and they are in the same side of the triangle. So they both lie on a circle which also contains B and C. This is the converse of inscribed angle theorem. Well, so the conclusion is pretty interesting. BC HAH points BC HAH or concyclic. Now let's use this diagram to derive something more fascinating. So here we go with the circle that we are trying to analyze. We introduced this circle by proving that angle BHAC equals angle BHC. Both are 180 minus A. So this property can be used to derive the angle BHHA. Let's take a closer look. Let's find angle HHAC. Since I know BHHAC is a cyclic quadrilateral, the opposite angles are supplementary. Now this implies angle HHAC and HBC are supplementary. I know that HBC equals 90 minus C. The reason is because when you extend BH, then it forms an altitude on the side AC. And this angle is C, therefore angle HBC must be 90 minus C. Therefore, due to the supplement angle argument, angle HHAC must be 90 plus C so that their sum is 180. Alright, so this is 90 plus C. Now, here is the twist. Join AH and let's extend it. I know that angle AHAC will be 180 minus C. This is something that we derived at the start. As you could see, angle AHAC is 180 minus C. That is this angle. Therefore, the angle made by the extended ray AHA with CHA will be C. So therefore, the angle that remains in CHAH will be 90 degrees. And thus we conclude that angle HHA is 90 degrees. So this is derived by subtracting the angle C. That is, angle HHA is nothing but 180 minus of angle HHA, and let's call this angle to be let's call this point to be T. So HHAT, and HHAT will be 90 plus C and minus C, because we subtract this C from this 90 plus C. Therefore, we get 90 degrees. And this proves that HHA is perpendicular to AHA. But AHA is the A median. This is a property we derived in the second episode. So, thus HHA is perpendicular to the A median. And what does that imply? We have located the point HA on the A median. HA is the foot of perpendicular from H to the A median. It is the foot of perpendicular from the orthocenter of the triangle to the A median. So this means we can locate the A Humpty point as follows. You just draw the median and consider the orthocenter. Orthocenter is the intersection of altitude. Intersection of altitudes. All altitudes concur at this point, and we draw perpendicular from H to this median. Let's say AMA is the median, where MA is the midpoint of BC. Then this point will be the A Humpty point. Now, this similar definition can be carried forward for B median. So we draw the B median and we draw perpendicular, and voila, we get the B Humpty point. And we draw the C median to MC, and we draw perpendicular from orthocenter to get the C Humpty point. Because all these are symmetric definitions and can be easily addressed by just changing the letters. Now also notice that all these points, and this is the centroid G of the triangle, which is the intersection of medians. Notice that all these Humpty points lie on the circle defined by HG as the diameter, because the angle H to any Humpty point to G is 90 degrees, and therefore they all lie on the circle with diameter HG. So this is a very beautiful property. You can also comment your own ideas in the comments. In the next episode, we will define Dumpty point and few basic definitions and properties of it. So Stay tuned. Happy learning. Bye.